Welcome to the screencast on humidity charts, also known as psychrometric charts. Hopefully we will cover some examples on how to use these charts, how to go reading through them so that you can utilize them efficiently in problem solving water-air systems. In Felder and Rousseau, in the third edition, they have two charts, figure 8.41 and 8.42, which are on pages 385 to 386. These are both for SI and American engineering units. Now, I will predominantly work with the SI units in this video just to keep it fairly simple. It's important to note that this chart that you're looking at for SI units uses two reference states. One reference state for water, being a liquid at 0 degrees Celsius in 1 atmosphere, and the reference state for dry air, being at 0 degrees Celsius in 1 atmosphere. Now let's start by introducing a few terms that are worth noting. The dry bulb temperature, which is reported on the x-axis, is the temperature of the air as recorded by a thermometer. Now this chart goes from negative 10 degrees Celsius to 55 degrees Celsius. Absolute humidity is the amount of water in the air, or also known as the moisture content. This makes up the y-axis. Now we've seen something like this kind of before, where we use the saturation pressure of water at a given temperature over the total pressure to determine the mole fraction of water in air. And this is just converted over to a mass fraction, where we have the mass of water per mass of dry air. Relative humidity is the relation of the actual moisture content to the saturation content of a given temperature. The leftmost line of this chart represents saturation. Now, if we look at the other lines that are kind of run parallel, we see that that would be a line for 20% relative humidity. This would be a line for 40%, 60%, and so forth. So given a certain temperature and relative humidity, you can easily see what the moisture content of that air would be. The dew point can be determined if you cool your system, moving horizontally to the left until you reach saturation. If I chose 25 degrees Celsius and say 50% relative humidity, then we would fall right here on this chart. Now the dew point temperature for that system, we would cool our air down until saturation. This temperature is about 14 degrees Celsius. So given air at 25 degrees and relative humidity of 50%, the dew point temperature would be 14 degrees Celsius. Let's try the following problem. Find the dew point of an air-water system if the dry bulb temperature is 80 degrees Fahrenheit and the relative humidity is 50%. Since we're given Fahrenheit, we can either convert to Celsius or use the American engineering chart. We go to 80 degrees Fahrenheit and 50% relative humidity. We're going to say that that falls right about here. If we follow horizontally until saturation, we get to about 58 to 59 degrees Fahrenheit. So the dew point temperature of that system is about 58 to 59 degrees. We could also determine the enthalpy of an air-water mixture. Again, this is relative to the reference state. If you move along the diagonal line up to the left, you can read what the enthalpy is. So, for instance, that initial system, we can move upwards to the left, and our enthalpy would be somewhere between 31 and 32 BTUs per pound of dry air. So let's try an example problem where we need the enthalpy of our air. And I'm going to go back to SI units. If a tank contains 10 kilograms of saturated air with a relative humidity of 100%, the dry bulb temperature is 20 degrees Celsius. Find the enthalpy of this mixture. Alright, so we can start at 20 degrees Celsius in saturation. Moving right up to 20 degrees to our saturated line. The enthalpy of this mixture is about 57.6 kilojoules per kilogram of dry air. We know that at this point, we follow it to our moisture content, and we get a moisture content of about 0.015 kilograms of water per kilogram of dry air. This tells us that we have, after recalculating, a mass fraction of air of about 0.985. We can multiply that by our 10 kilograms that we start with to get about 9.85 kilograms of dry air. Multiplying that by our enthalpy of our air, we can figure out what the enthalpy of our mixture is. This comes out to about 567 kilojoules. We can also determine the amount of heat to raise the temperature of the system using these enthalpy readings. Let's try the following example. A saturated mixture contains 100 pounds of dry air. How much heat is required in BTUs to raise the dry bulb temperature from 30 degrees Fahrenheit to 70 degrees Fahrenheit? If we go back to one of our American Engineering Unit charts, we could read at 30 degrees Fahrenheit saturation right about here. We have an initial enthalpy of about 10.9 BTUs per pound dry air. Now we need to raise the dry bulb temperature from 30 to 70, so we move horizontally until we get to 70 degrees. Then we read the enthalpy at that point. If we take that line up so that we can read the enthalpy, we get about 20.8 BTUs per pound dry air. So we know our change in enthalpy is going to be 9.9 BTUs per pound of dry air. We're told that we had 100 pounds of dry air, so our Q, or heat, needed to do this would be 990 BTUs. The charts also provide the humid air volume written down here, which is pretty much the specific volume of the mixture in terms of meters cubed per kilogram dry air on the SI unit graph. Now these are these diagonal lines with negative slopes, in which then you can read what the volume of the air and water take up. When you use these values, you need to make sure that you're using the correct units to convert to figure out the actual volume of your air. So it may be helpful to use the moisture content so that you can calculate based on a humid air back and forth from a dry air. There's two more features on these charts that I'd like to go over. One is the wet bulb temperature, which is one of the harder attributes to grasp and said to be best defined by how it's measured. A thermometer bulb is wrapped in a porous cloth and soaked in water so that it's saturated. As air moves past this bulb, water will evaporate, and the heat associated with this evaporation will cause a decrease in the thermometer temperature. The final temperature reading upon equilibrating, assuming that the cloth still stays saturated, is the wet bulb temperature. Thus, you can see or realize quickly that in a saturated environment, the wet bulb and dry bulb temperature are the same, since no evaporation will occur. Now, if we go back to our problem where we have, say, 25 degrees Celsius air at 50% humidity, we can figure out that the wet bulb would just be following these lines up to the saturation point. So our wet bulb temperature is about 18 degrees Celsius, meaning that 50% relative humidity air at 25 degrees Celsius would cause enough evaporation to occur such that the surface temperature, that wet bulb temperature, would actually read 18 degrees. You can kind of think of this like when you get out of a pool. Your body's wet, and as it starts to evaporate, you get colder. So obviously you're going to feel colder depending on the relative humidity of the air. So let's try the following. Two large containers initially contain dry air at 40 degrees Celsius. A small amount of water is added to container 1 so that the relative humidity becomes 30%. Let's see where that would be on this chart. Right about here. That's container 1. Water is also added to container 2 such that the relative humidity becomes 80%. Just go right up that line all the way up to 80, which obviously is outside of the chart. Based on these two conditions, which would have a lower wet bulb temperature? Well, even though we can't see what's up at 80% humidity for that case, we do know that following these horizontal lines, this wet bulb temperature for container 1 would be much lower than the wet bulb temperature for container 2. So we can safely say that container 1 has a lower wet bulb temperature. The last thing I want to mention on this is the enthalpy deviation. For non-saturated systems, you could account for the difference in enthalpy from the saturated state by adding the correction term written on these plots. You can see the correction term by these other lines that kind of run vertically up the graph. So for instance, if we had, say, 30% relative humidity air at 30 degrees Celsius, we would be right along that correction term for the enthalpy deviation. So that when we read the enthalpy, which is say about 51 kilojoules per kilogram dry air, we add this correction term, negative 0.4, so that our enthalpy of the system may actually be about 50.6 kilojoules per kilogram dry air. This is a nice quick way of figuring out for non-saturated systems what the enthalpy would be for these systems. Hopefully that helps you understand these charts a little bit more, and now you feel confident using them in your future work.